Let's look now at section 2.7 and talk about analyzing graphs. In this section, we've seen a little about creating graphs from modifying parent functions by using transformations. In the next chapter, we're going to be looking at adding details to these graphs. In fact, a lot of detail compared to what we have now. But before we do that, let's talk about an analysis of functions. Let's talk about looking at a function's graph and trying to describe it, trying to talk about it. The reason we want to do that is because if we know the correct language and how to describe these graphs, then we'll know exactly what we're looking for when we create our own. Essentially, we're going to study some graphs and talk about their properties, and in doing so, we're going to learn what the different properties of graphs can be. That way, when we actually see graphs in full detail and make graphs in full detail, we'll have a better handle on what can and cannot happen, what should and should not happen. Right? This section, you'll note, doesn't have a lot of computation to it. There won't be a lot of computing numbers or anything of that nature. This is largely a vocabulary section where we're going to learn what things are called, what the appropriate definition is, and things like that. In the coming sections, we'll be using a lot of this language, so we're going to want to take some time to properly define them. So first of all, let's talk about symmetry. Most graphs won't have any kind of symmetry. Okay, well, what is symmetry? Symmetry involves a reflection. It involves having part of your graph be the same reflected to another part of your graph. Most graphs won't have any kind of symmetry. For example, a graph that looks like this won't have any kind of symmetry. And most of our graphs will just be some line or collection of lines that don't have any relationship between one part of the graph and another directly, at least not a visual relationship. However, some graphs will have some type of symmetry. The three kinds of symmetry that we're going to look at here are symmetry with respect to either axis, the x-axis and the y-axis, and then sort of a combination of those, which is called symmetry with respect to the origin. So first of all, let's talk about symmetry with respect to the x-axis. When we say something is symmetric with respect to the x-axis, we mean that the x-axis is going to behave like a mirror. Anything that's above the x-axis will also exist in a mirrored form below the x-axis. So, for example, if we have a graph that has this part, and let me go ahead and do that in a different color. That should be fine. If we have a graph that looks like this, then if that graph is symmetric with respect to the x-axis, then we should also have this portion, where this is being reflected across the x-axis. Okay? Now, if instead of reflecting the graph across the x-axis, if we reflect it across the y-axis, so for example, this would be reflected this way, this is a graph that is symmetric with respect to the y-axis. With respect to is a phrase that shows up a lot, and it's also kind of a long thing to write out. So WRT stands for with respect to. In other words, that's the thing that's acting like a mirror. So here, this is symmetric with respect to the y-axis. Okay. Now, the third kind of symmetry that we look at when we look at graphs is symmetry with respect to the origin. Symmetry with respect to the origin is sort of a combination of these two. If something is symmetric with respect to the x-axis, so let me start with this piece here. If something is symmetric with respect to the x-axis, that means it's being reflected across the x-axis. It would be down here. Now, if something is symmetric with respect to the y-axis, it will be reflected across the y-axis, and we have this piece over here. We've seen both of those. If something is symmetric with respect to the origin, then this piece is being reflected in both of these ways. Here, take this, reflect it first with respect to the x-axis. That brings it down here. Now take this piece and reflect it with respect to the y-axis. That would bring that over here. If you did it the other way around, if you started with this and first reflected with respect to the y-axis, that would bring you over here. And then, if you reflect this piece with respect to the x-axis, that would come down here and still give you this piece here. This is what's called symmetry with respect to the origin. It's essentially both of these at the same time. First you reflect across one line, then the other, and once you've done both reflections, that piece is symmetric to this piece across the origin. Okay. Now, how do we know if this is the case? How do we know if something's symmetric with respect to the axis or the origin? Well, just visually look at that. Well, yeah, but what if I don't have the graph? What if I have an equation? Well, one thing we could do is make the graph. Well, yeah, but sometimes making a graph is going to take a lot of work. In the graphs that we've seen so far, we've modified a parent function. But in later chapters, we may have some that require a little bit more effort than that. So sometimes creating a graph is something very short and simple, like we've seen in the last section. It takes 1 or 2 steps. Other times it can be a lot more complicated. So yeah, creating a graph is an option, but sometimes it's a little bit longer than what we would like. So from an equation, we can figure out whether or not something is symmetric with respect to the x-axis, y-axis, or the origin. Here, one thing to note is if something is symmetric with respect to the x-axis, if you have a point on one part of the graph, and here I'll just call this x comma y, notice that because this gets reflected down this way, that automatically means that this point down here, which has the same x value, but the opposite y value, namely x comma minus y, would also be part of your graph. So that's one way of checking if your graph is symmetric with respect to the x-axis. Essentially, if you can replace a y with a minus y and still have a result that's on your graph, then that graph is symmetric with respect to the y-axis. With respect to the x-axis. With respect to the y-axis, you have something similar, except with the other variable. Here, if this is the point x comma y, if this graph is symmetric with respect to the y-axis, then that means that this point must also be on the graph. Notice those have the same y variable, but if this is a positive x, this one will be a negative x going in the other direction. Like that. And note that this one, if this is the point x comma y, then this point over here would be opposite this way, but also this way. So here we would have negative x comma negative y. All right. So this gives us a test for symmetry. Oops. There we go. Substituting y, I guess I should say minus y. Substituting minus y for y gives an equivalent equation. In other words, it doesn't matter if you have y or minus y, both points should still be on the graph. For symmetry with respect to the y-axis, we have something similar except with the x variable. Substituting minus x for x gives an equivalent equation. And symmetry with respect to the origin, both are going to be true. Substituting minus x for x and minus y for y gives an equivalent equation. So let's see an example of that. So let's consider the equation, the absolute value of x plus y is equal to 4. Okay? So this is an equation, and we could take the time to graph this. After all, we do know what the graph of the absolute value function looks like, and we could modify it to see if we can't create a graph. But that may take a bit of time. And here, the question doesn't require us to make a graph. It's one option, but here all we're being asked to do is determine the symmetry. Note that it is possible not to have any symmetry. So just because you're told to determine the symmetry, that doesn't mean it has to be one of these three. It's possible you don't have any symmetries. Okay. So here, the way we test this is we're going to substitute in minus y for y. And we're going to see if it makes a difference. We're going to do the same thing for minus x and x. And then we'll do the same thing for both at the same time. So here we're going to check, is this symmetric with respect to the x-axis? All right. Is it symmetric with respect to the x-axis? Well, it's symmetric if replacing minus y for y gives an equivalent equation. So let's do that. Let's take this equation and let's replace the minus y. Let's replace y with a minus y. So this becomes absolute value of x. And now instead of saying plus y, well, that's a negative now. So that's minus y equals to 4. Notice these are not the same equation anymore. By replacing y with minus y, we end up with a different equation. So that means that here, it does not give you an equivalent equation. It's different. So here, no, you don't have symmetry with respect to the x-axis. All right, let's check symmetry with respect to the y-axis. If something is symmetric with respect to the y-axis, that means substituting minus x for x will give us an equivalent equation. All right, so let's do that. Let me replace that x with a minus x plus y is equal to 4. Notice I can simplify that. After all, the absolute value of a number is always positive. So here that negative is going to go away. And I get the absolute value of just positive x. All right. The absolute value will make that go away, the negative. Gives me just a positive x. Plus y is equal to 4. Oh, notice, even though I replaced x with minus x, after I simplified, I still ended up with what I started with. So here, replacing an x with a minus x doesn't make a difference. Oh, so replacing an x with a minus x gives me an equivalent equation. So here, yes, this is symmetric with respect to the y-axis. Now, it is possible for a function to, or for a graph to be symmetric with respect to more than one of these. So here, even though we already found it's symmetric with respect to the y-axis, let's check to see if it's symmetric with respect to the origin, because it's possible to be symmetric with respect to more than one of these. So let's go ahead and check the third one. To check if something is symmetric with respect to the origin, basically we're doing both of these. We're replacing x's with minus x and y with minus y. So here that's going to be minus x in the absolute values, and then plus a negative y, which we can just write as minus y, is equal to 4. Taking the absolute value of negative x is the same as taking the absolute value of positive x. Minus y is equal to 4. And notice that here, that's not the same equation anymore. So here, replacing both x with minus x and y with minus y does make a difference. I don't get an equivalent equation. So here, no, you don't have symmetry with respect to the origin. So here, the question is determine the symmetry. The answer is the equation, or the graph of the equation. The graph of the equation is symmetric with respect to the y-axis only. Okay. Now notice a moment ago I said function, and I caught myself there. This does not necessarily involve a function. In fact, right here, you'll notice that this graph couldn't possibly be a function because it does not pass the vertical line test. Notice, if I pass that vertical line through the graph, it crosses at more than one point. And so, by the vertical line test, here y would not be a function of x. Okay, here it would be, and here it would be. Well, yeah, but any graph that is symmetric with respect to the x-axis would have the same problem. Because if you're symmetric with respect to the x-axis, that means that you're always going to have points that are right on top of each other. Symmetry with respect to the y-axis or with respect to the origin don't have that problem. So what that means is that if we're talking about just a graph of any particular graph, then you can have all three of these symmetries. Maybe none, maybe just one, or maybe two, or maybe all three. But if we're talking about specifically a function, which is what we're going to be doing for most of this course, we care more about functions than any other kind of equation, then we restrict ourselves to only two types of symmetry. It's not possible for a function to be symmetric with respect to the x-axis. For a function, it can only be symmetric with respect to the y-axis or the origin. We give these names. So, definition. Let f of x be a function. It doesn't have to be any particular function, just a function. Okay, so f of x is a function. If f of minus x and f of just regular x are equal to each other, or in other words, if I replace an x with a minus x and nothing changes, well, that sounds familiar. If I replace an x with a minus x and nothing changes, then my function will be symmetric with respect to the y-axis. That's called being an even function. Then f is called an even function. And here, that's what we're defining. We're defining what it means to be an even function. And here I'll make a note. Note, even functions, again, we see that from the previous example. Even functions are symmetric with respect to the y-axis. Okay. Now, the other possibility is if f of minus x is equal to the opposite of f of x. Here, we replace x with minus x. And here, well, remember, f of x is the same as saying y. So here, the positive y is equal to the negative y, right? What does that mean? Essentially, that means if you replace x with minus x and y with minus y, everything's still equal. There's been no change. Oh, but we saw that too. If you replace x with minus x and y with minus y and nothing changes, everything's equivalent, then your graph of that equation will be symmetric with respect to the origin. So here, if f of minus x is equal to minus f of x, then f is called an odd function. Okay? And again, note, odd functions are symmetric with respect to the origin. Functions cannot be symmetric with respect to the x-axis. Okay. For now, the name even and odd, those are just names. For those of you who follow us through past algebra, into trigonometry, and into calculus, these names start to make more sense in calculus. Even and odd functions, for now, just they're labels. Don't worry about that. It doesn't involve even or odd numbers right now. Just consider them labels. Okay, so let's take a look at some examples of that. Let's say I have a function. So determine if the function is even, odd, or neither. It is possible for a function to be not even or odd. Now, it can't be both, because if it's even, that means f of minus x is equal to f of x. If it's odd, f of minus x is equal to minus f of x. It can't be both, right? Either f of minus x is equal to that one, or f of minus x is equal to that one. If you have a function, it can't be both. Right? So it's either even, odd, or neither. You won't have any that are both. So let's see. Let's say f of x is equal to 4x squared minus 3 times the absolute value of x. Just like that. Okay. Here, the test to see whether or not a function is even or odd or neither is to do this. F of minus x is either going to equal to this, or it's going to equal to this, or neither. Oh, okay, so what we want to do is we want to find what f of minus x is equal to. Okay, so first of all, let's find f of minus x. Okay, f of minus x means, remember how function notation works, all of our x's are going to be replaced with minus x's. So this is going to be 4 times negative x squared minus 3 times the absolute value of negative x. And now we can simplify. When you square something, you're multiplying it times itself, and a negative times a negative becomes a positive. So that's 4 times positive x squared. And here, the absolute value of a number has to be positive. So the absolute value of minus x is the same as the absolute value of just regular x. So that's going to be minus 3 absolute value of x. Notice how, when I plugged in minus x here, I ended up with the original function. So here, this is equal to f of x. Oh, okay, so f of minus x is equal to f of x. But our definition tells us if f of minus x is equal to f of x, that's an even function. So here, f of x is even. Like that. Okay. Let's do another one. Let's take g of x. Let's say g of x is equal to x over x squared plus 1. Okay. Once again, we're going to test to see if the function is even or odd by substituting in minus x in place of x and seeing what happens. So let's say g of minus x is equal to, okay, well that x is replaced with a minus x, and this x is replaced with a minus x, just like that. Okay, well here the minus x is just, it's a minus x, that's what it is now. But here minus x squared, when you square a negative, you get a positive. So this will give us minus x over x squared plus 1. Notice that that's not the same as my original function, right? It's a little bit different. Okay, so if it's a little bit different, that means it's not the same. Okay, so g of minus x is not the same as g of x. Okay, so it's not going to be even. What about odd? Well, if I substitute a negative x, I'm supposed to get the opposite of my original function. Okay, well here, what was the opposite of our original function? If g of x is equal to x over x squared plus 1, then that means that the opposite of g of x would be, you would take this and take its opposite. Okay, well, this is a positive, so let's make that a negative. So this would be the negative of x over x squared plus 1. Oh, yeah, but that's what that is. That's negative x over x squared plus 1. So here, g of minus x is not exactly the same as the original function, but it is the opposite of the original function. Okay, so since g of minus x is the exact opposite of the original function, oh, then by our definition, that makes that an odd function. So g of x is odd. Just like that. Note that your function doesn't have to be even or odd. For example, if h of x is equal to, let's keep this simple. Let's say x squared minus 5x. Okay. Let's go ahead and find h of minus x. All right, so substitute in negative x there and there. And that'll give us negative x squared minus 5 times negative x. Okay, if you square a negative, that's a positive. And negative times a negative, that's also a positive. Okay. So notice these are not exactly the same. H of x and h of minus x are not equal to each other. Okay, so then that means it's not even. Okay, but now maybe it's equal to the opposite. All right, well, what is the opposite? If h of x is equal to x squared minus 5x, then the opposite of h of x, well, that would be the opposite of all of this stuff. Okay, well, you could distribute that negative. That would be minus x squared, and double negative makes that a plus 5x. Well, that's not the same either. Notice h of minus x, that's not equal to the original function, but it's also not the opposite of the original function. Okay, so then it's not even. It's also not odd. So here, h of x is not even or odd. And that's fine. There's going to be functions that aren't either. Okay, so now the next thing we want to do, let's talk about the behavior of a function. Sometimes mathematical language is a little strange. When we talk about functions, sometimes we talk about how does the function behave, almost as if it were alive. So let's go ahead and start with some definitions here. Let's start off with a function. So just let f of x be a function. All of this stuff might apply to graphs of equations that are not functions. We're not going to worry about that. You might have an equation that doesn't generate a function. Right now, we're just going to stick with functions. Let f of x be a function. And let I be an interval in the domain of f. Let what now? What does that mean? Well, first of all, we're starting off with a function. Now remember, every function has a domain, meaning all the x values that you could plug into the function. Now the domain might be something like from negative infinity to infinity, or it might be something like 1 to 50. Right? You have some domain, some group of x values that can be plugged into your function. When we say let I be an interval in the domain, all that means is we're going to take an interval in the domain of f. It might be the whole domain, but it doesn't have to be. You can have a small little piece of the domain. And we're going to label that little piece. We're going to label it I. So as a visual, as an illustration of that, let's say I have this function here. And let's say it's the function that starts at this point. It's going to go up and then come back down and stop right there. Okay. So here, let's say that's the number 1 and that's the number 10. Okay. So now, the domain of this function is every number between 1 and 10. All right, so that's my domain. When we say I is an interval, when we say I is an interval in the domain of f, all we mean is, okay, now take some interval from this domain. Now, if you want to, you could just pick the whole domain. But sometimes it's not convenient or sometimes it's not useful to do so. Sometimes you want a smaller piece. So for example, I could say, okay, here's a little interval inside the big one. Let me just take the numbers between 2 and 4. Okay, so here's one interval inside of the domain, right? Here's the whole interval. We can take a little piece from the inside of the interval. This little piece, we're going to call it I. Right? Right now, we're not going to be specific about what that interval is. We'll see that in the examples, and it'll vary depending on the example. So for now, we're not going to be specific and say, oh, we want the interval, 1 to 5 or 2 to 20. Here, we're just going to say, okay, it's just some interval which we're going to call I. We'll be more specific for specific problems. Okay? So let f be a function and let I be an interval in the domain of f. So now we're going to define three different things within this definition. If f of x1 is greater than f of x2, when x1 is less than x2, let's see, that's grammatically backwards. Let me write it starting here. Thankfully, I have a little space here. Let's see. So the function f is said to be decreasing in I if f of x1 is greater than f of x2 when x1, I guess I should say for all, not when. For all x1 less than x2 in I. Okay, what does that mean? Okay. Let's say I have a function and it's got a domain, but we don't care about the whole domain. We just care about a little piece of the domain, an interval I. So I'm not even going to bother to draw the whole function. I'm just going to worry about the part here in the interval I. Okay, now notice that in the interval I, we want two numbers. One of them we're going to call x1, and the other one we're going to call x2. Okay, here x1 is less than x2, which means it's to the left. So here, your x1 would be maybe right there, and your x2 would be maybe right there. Okay. All right, now, f of x1, remember what that means. That's the y value. So if you take this and plug it into your function, you're going to get some y value up here. So if this is x1, plug it in, and up here you have f of x1, your y value. Now, if f of x1 is greater than, or in other words, higher than what you get when you plug in x2, so this would be f of x2, if this point is higher than this point, and if that's always the case for every point in I, for every point in this region, then the function is said to be decreasing. Visually, the way that looks is as you look at the graph from left to right. That's what this part's telling us. You're going from left to right, from smaller to larger. If you look at the graph on the interval from left to right, the graph should be getting lower. The y value should be getting closer and closer to the x-axis. It should be going downhill. If your y values keep getting smaller and smaller as you move toward the right, then the function is said to be decreasing. Okay. So that's the first thing we're defining. We're defining what it means to be decreasing. Increasing is almost the same definition, but we're going to flip one inequality, because for decreasing, as you go from left to right, you want it to be going down. For increasing, as you go from left to right, you're going to want it to go up. So here f is said to be increasing in I if f of x1 is less than f of x2 for all x1 that's less than x2 in I. So it's pretty much the same thing, except now you're saying, okay, you have your interval I, you have your x1, which is somewhere on the left, and you have your x2, which is somewhere on the right, because it's x2 is greater, so it's further to the right. Now, your f of x1 is less than your f of x2, which means your f of x2 is going to be higher. If that's always the case, if every time you're going from left to right, your y value is going up, then the graph is said to be increasing. All right? The last one, you say, well, what else could it be? It's either going up or going down, right? Increasing or decreasing? Well, it's possible that it's not doing either. F is said to be constant in I if f of x1 is equal to f of x2 for all x1 and x2 in I. Or in other words, it doesn't matter what points you pick. It doesn't matter what x1 and x2 you pick. You're always going to have the same y value. That means the graph's never going up. It's never going down. It doesn't matter if you have this x1 and this x2 or any other ones. Your y value is always exactly the same. So your graph's not increasing or decreasing. That's constant. Okay? This is a way of describing the behavior of a function. This is one type of behavior, whether a function is increasing, decreasing, or constant. Note that your function doesn't have to behave just one way. This original illustration I had here, your graph is going up for part of it. Notice, as I move from left to right, the graph is going up, so it's increasing. But then, once you reach this point, then, as you continue to go to the right, then it's decreasing. So that doesn't mean this function is two different functions. It just means the function behaves one way for a little while, and then it changes its behavior. All right? So how do I describe that? How do I describe the behavior of this function? It's not increasing, it's not decreasing, it's both. So how do I say that? So let's look at an example. Here, I'm not going to give any kind of equation. For now, let's just stick with a graph. So that's 1, 2, 3, 4, 5. And let's go down here, -1, -2. And here, let's do 1, 2, 3, 4, 5. And then back here, -1 and -2. All right, so let's go ahead and draw a graph. And I'm going to have a graph that comes up from over here. It's going to come down until we reach this point. And then from here, it's going to come up until we reach this point. Like this. And then once we reach this point, it's going to be flat for a little while. And then once we reach this, it's going to go down like that. Okay? So here, let's describe this behavior. Okay, well, here, it's, now, you got to be careful. Right here, a lot of people will make the mistake of seeing the little arrow and saying, oh, that must be increasing because the arrow is pointing up. That's not how that works. By our definition, when you talk about something being increasing or decreasing, you always look at it from left to right, from the smaller x value to the larger one. So here, even though the little arrow is pointing up, that doesn't mean the function is increasing, because when you talk about increasing or decreasing, you're following the graph from left to right. And notice if I draw it from left to right, it's actually going down. So be very careful with that. Don't let the arrows trick you. The arrow is just saying that it keeps going in that direction. But for the purposes of increasing or decreasing, we look at it from left to right. So here, I note that, okay, well, yeah, it's decreasing. And then if I keep going left to right, it's increasing. And then it's constant. And then it looks like it's decreasing again. Okay, so there we go. I've described it. Well, yeah, but aren't there other functions that could do the same thing? I mean, I could have something that decreases and then increases and then is constant and then decreases again. And that looks completely different from this. So how do I tell the difference between those? Right? It's not enough to just say it's increasing, then decreasing, then constant, then decreasing. So I need to be more specific. How much does it increase? Where does it increase? So whenever we describe if a function is increasing, decreasing, or constant, we do it using an interval. We say, over what interval is it decreasing? Here's the way that's going to work. So let's just pick on this one for now. Oh, actually, let's start with this one. here my function is increasing. It starts increasing here, and it finishes increasing right here. So it's increasing everywhere between these 2 points. The way we're going to express that is using the x value, meaning, okay, what's the x value of the point where you start increasing? Oh, that x value is -1. Okay, now it continues to increase until we get here. What's the x value of the point where you finished increasing? Oh, that's +1. So when we talk about this function, we say it's increasing on the interval from -1 to 1. Like that. Now you might say, well, wait a minute. Those points are part of the graph. Why did you use round parentheses? Shouldn't it be a square bracket? Well, the problem is this point, okay, my function's increasing. Oh, now the next part of my function is constant. Okay, so which one does that point belong to? I mean, that's the last point where it was increasing, but it's also the first point where it was constant. Same thing with this one. This is the first point where it starts to increase, but it's also the last point where it ended the decrease, where it stopped decreasing. So where does this one belong? Does it belong to this part or to this part? So instead of arguing about it, instead of trying to determine, okay, which one does it belong to, it kind of belongs to both. So we kind of say, okay, don't worry about that point, just the stuff in the middle. So the function is increasing on the interval from -1 to 1. Okay. Now what about constant? Well, again, it's constant between here and here. So what's the x value? Well, that's 1. And it continues to be constant until we get to this point. And the x value here is the number 3. So here my function will be constant on the interval from 1 up to 3. And now decreasing, it's decreasing in 2 separate parts. Here it's decreasing from here to here. Since that keeps going on forever, it never really has a first point. It goes on forever to the left. Oh, but we have a symbol for that. That's -infinity. This is decreasing on the interval from -infinity, and then it stops decreasing once we get to -1. Oh, but that's not the full answer. Look, it's decreasing over here too. It starts to decrease again when we're at this point, which has an x value of 3. Starts decreasing at this point, which has an x value of 3, and then it continues to decrease forever. Okay, so out to infinity. And if you think back to chapter 1, the way we describe an answer that has 2 separate intervals together as one answer, we use the union symbol. So here your function is increasing on the interval from -1 to 1. It's constant on the interval from 1 to 3. And it's decreasing on the interval from -infinity to -1. And also from 3 to infinity. Just like that. So give that a try. Take the following graph and go ahead and describe it. See if you can go ahead and describe the intervals over which the graph is increasing, decreasing, or constant. All right? Here, all of these are meant to be whole numbers. So here, if it looks like it's at 5, it's at 5. I'm not going to say, oh, that's really 4.99. No, if it looks like it's at a whole number, it's at a whole number. So take a minute, go ahead and pause the video and see if you can't describe where the function is increasing, over what intervals it's decreasing, and over what intervals it's constant. Once you have a result, go ahead and unpause the video and we'll go through it together. Okay, so let's take a look here. Let's talk about where it's constant first, then decreasing, then increasing. There's no reason I'm doing it in this order. I have to go through all 3, so I'm just going to go ahead and do them in this order. All right, so where is it constant? All right, well, right here. It's not going up or down. It's a perfectly flat line. So it starts to do that when the x value is 5, and it continues to do that forever. Okay, so starting at 5 on to infinity. Remember, this point, we're not going to argue over whether it's part of this or part of this. So here we don't worry about the endpoints ever. function's constant from 5 to infinity, and we only worry about the stuff inside the interval. Decreasing. Well, it's decreasing here and here. Remember, don't let the arrow fool you. Even though it's pointing down here, this is increasing because you always look at things from left to right. And if I follow this left to right, it's actually going up. So here, decreasing, that's going down, and that's going down. So this starts to decrease when the x value is 0, and it stops decreasing when the x value is 2. 0 to 2. Okay. Notice, we don't care about the y values ever. We don't say, okay, it went down to 1. It went down to a y value of 1. We don't care. When we're describing whether a function is increasing or decreasing, you use the x values over which it's increasing and decreasing. Same thing over here. Yeah, it starts up at a height of 5 and comes down to a height of 3. But that's not how we describe it. We say, okay, the x value over where it starts to decrease is 4, and it continues to decrease until the x value is 5. So here this will be decreasing from 4 to 5. And since it's decreasing over several intervals, the union of those intervals gives me my result. And I said the question, I never actually wrote it down, did I? Describe where the function is increasing, decreasing, or constant. You could also say describe the behavior of the function, but here let's be a lot more specific. There are other behaviors besides this. Okay, finally, where is it increasing? Well, again, this part, but also this part. So here, it starts to increase. Well, it never really starts. It was always increasing, all the way back here from the left. Okay, so that's from negative infinity. And it continues to increase until you reach this point, which has an x value of 0. Yes, it goes up to the y value of 2, but that's not how we describe it. We describe it using the x values, from negative infinity to an x value of 0. And then again, it starts to increase when your x value is at 2, and it continues to increase until your x value is at 4. And there we go. This describes where our function is constant, where it's increasing, and where it's decreasing. Let's use this graph for one more type of example. Here, let's give one more definition. Let's begin with a function. Again, let f of x be a function. And let a be a number in the domain. All right, so here a is just some number you could plug in for x. It doesn't matter what number it is as long as it can be plugged in. So let f of x be a function and let a be a number in the domain, I should say the domain of f. Okay. Then we have a two-part definition here. A comma f of a is called a relative maximum of the function f if there is an open interval. And again, an open interval is just an interval that doesn't include the endpoints. We're looking at these kind of intervals. If there is an open interval, it doesn't say which one, as long as there is one, an open interval containing the number a, such that f at a is greater than or equal to f of x for all x in the interval. Okay. And then here I'll explain this here in just a moment, but first let's go ahead and give the other part of the definition. A comma f at A is said to be a relative minimum of f if there is an open interval. Oops, I never put the word interval here, did I? Is an open interval containing the number A such that f at A is less than or equal to f at x for all x in the interval. Just like that. Okay, so what this says is you have a function and you have a number in the domain of the function. You have a function and you have a number that's in the domain of the function. It's something that could be used as an x value in that function. Now, here, this function can keep going forever and ever and ever, but all I care about is, can I find an open interval around A? Okay, so just a little piece here. Just, that part there. Just that part there. Okay, in this illustration, this point right here, A comma f at A, is called a relative maximum of a function. Why? Because for every x value, for every number in this interval, if I plug in those numbers, any of them, into my function, I'm either going to get that point up there or some point that's lower. Notice that this is the highest point in that interval. That's what this means. It means that f at A is either going, that for every x value in here, either I'm going to get that point at the top or I'm going to get something smaller, right? F at A is going to be greater than f of x, so all the other f of x's are going to be somewhere slightly lower. Whenever we talk about relative maximum, we're essentially talking about the top of a hill. Note that it doesn't have to be the biggest point in the entire graph. It just has to be the biggest point around here. Because here we're looking at as long as there exists an open interval. So for example, let's say I had this graph continue until I got this. Well, yeah, that's the biggest point around. This one's a lot smaller. But because I can find an open interval around that point, where in that interval, that's the biggest point around, that's the tallest point around, then even though it's not the biggest point of the entire graph, that's the highest point around here. So this would also be considered a relative maximum. Relative minimums say the same thing, but in reverse. Here, if every point is greater than f at A, or equal, in other words, if every point around this point is higher, well, then you have a relative minimum. That would be this one right here. So while both of these are relative maximums, this point right here would be a relative minimum because I can come up with an interval around that point where inside of that interval, I'm either at that point or every other point is higher. F at A is going to be lower than all the other f of x's. So it's lower than all the stuff nearby. And so this is a relative minimum. And just like with relative maximums, you can have more than one. When you describe a relative minimum or a relative maximum, notice you're describing a point. So you would say, okay, let's say this is the number 5. And let's say up here you have the number 9. Then the relative maximum would be 5, 9. It's a point. Right? So coming back up here, go ahead and give that a try. Given our definitions and given a intuitive definition of that, given an intuitive way of thinking about that, where relative maximums are the top of a hill and relative minimums are the bottom of like a little valley here. Go ahead and look at these points and see, can you find any relative maximums and any relative minimums? Go ahead and pause the video and give that a try. And whenever you are ready, go ahead and unpause and we'll look at them together. All right, and from just a quick look, we can pinpoint all of those. Here I have the top of a little hill, and same thing over here, I have the top of a little hill. So here, both of these would be local maxima. Here I have the bottom of a valley, and that would be a local minimum. Okay. So a local minimum, if you have more than one, it's local minima, M-I-N-I-M-A. Pluralization of minimum is minima. But here there's only one, so we can say minimum. The local minimum is, and here that's going to be a point, 2, 1. And here we're going to have a maximum, but then there's another maximum, so there's 2 of them. Here we're going to have a local maxima. Plural of maximum is maxima. And there's 2 of them. That's going to be 0, 2, and that's going to be 4, 5. And I just realized I've used two different words for this. Over here, I defined relative maximum and relative minimum. Another name for a relative maximum is a local maximum. Same thing for a relative minimum. It's another name is a local minimum. It depends on what textbook you look at. And well, frankly, I've actually gotten used to using local maximum and minima in our calculus class. That's the language they use. And for some reason, this book prefers to use relative as opposed to local. They mean the same thing. So my apologies if that caused any confusion there. Let me make a note of that down here. Note, local maximum and local minimum is another name for relative maximum and relative minimum. Those are both completely interchangeable. They mean exactly the same thing. It's just a matter of taste. And as you can see, I tend to use local maximum and local minimum, partially because I'm lazy. Local is 2 syllables and relative is 3 syllables. I find that easier to say. All right. So there we go. Your local minimum or your relative minimum, whichever you prefer, is 2, 1. And your local maxima or relative maxima is going to be 0, 2, and 4, 5. So this nicely describes our graph. It gives us a direction. Not only does it give us directions, it tells us, it's going up, it's going down, it's flat. It also gives us some points that tell us, okay, it's going up. Oh, and by the way, that's how high up it got. And then it starts to go down. And oh, by the way, that's the point where it bottomed out, and so forth and so on. Okay, the last thing we look at in this section are what are called piecewise functions. When we graph a function, we look at a single behavior, a single type of graph. If you think back to a previous section, we saw graphs that were quadratics, and we saw graphs that were linear, and we saw graphs that were cubic and absolute value graphs, and so forth and so on. We had a few different graphs and modified versions of those graphs. However, not every graph is going to have just a single behavior. Not every graph looks the same forever. These are called piecewise functions. Consider this graph. Let's say you had a graph that behaves like a line, like a straight line, like this. Okay, so that's got an equation. It's a linear equation. And in fact, that linear equation, it's got a slope of 1 and it passes through the origin. That's the simplest of all linear equations. That would be f of x is equal to x. All right? Slope is 1, so that's 1x plus, and then since it crosses through the origin, that would be 1x plus 0. You know, y equals mx plus b. In this case, your slope is 1, so that's 1x plus, and since your y-intercept is 0, 0, we could write that as 1x plus 0, or more simply just x. You say, okay, great. So you have the equation y equals to x, f of x equals to x. But why'd you stop there? Well, let's say once I get to that point, I no longer want it to behave like a straight line. Let's say now I want it to behave like a parabola. This is y equals x squared. Okay, so now f of x is not equal to x. It's equal to x squared. Okay, yeah, but these aren't two different functions. You say, yeah, they are. One's a linear function, one's a quadratic function. Well, no, there's two different behaviors. There's two different ways that the function behaves, but this is all one graph. This is all one thing. So how do I do that? How do I stitch together different behaviors into one function? So this is called a piecewise function. Here's how you do it. You say, okay, I know my graph is behaving like a straight line. Well, yeah, but it doesn't do that forever. Okay, so where does it do it? Well, it does it on this part. Well, how do you describe this part? Well, that's all the stuff that's to the left of 0. So from here that way. Well, we have a way of describing from everything from 0 to the left. That's everything from negative infinity up to 0. Right? So here, I know I want my graph to behave this way, but I only want it to behave this way when the x value is less than 0. So that's what I'm going to do. I'm going to say, okay, I want my function to behave like y equals x, but I only want that to happen whenever x is less than 0. Okay, but what if x is not less than 0? Oh, well, then I want it to behave this way. Or be specific. Well, I want it to behave like y equals x squared. But again, where do you want that to happen? Oh, I want that to happen when x is greater than 0. Okay, so here when x is greater than 0. Well, what about when it's equal to 0? Oh, well, right here I see that that I have that blue dot right there. So it looks like that point belongs to this part of my line. Oh, okay, so I want y to equal to x whenever x is less than 0, but also at 0. Okay, so less than or equal to 0. This is called the piecewise function. This brace is meant to keep this together, meaning this brace is meant to remind us that these are not two separate equations. They're not two separate graphs or two separate functions. They're just two parts of one function. In more advanced problems, you'll have 3 or 4 parts to this. So your graph might behave like a line, and then like a parabola, and then like a square root, or whatever. You might have different components. So this is called a piecewise function. A piecewise-defined function. And it's called that for, well, a fairly obvious reason. It's a function that's defined, that's described in pieces. Now here's one piece and here's another. So it's a piecewise-defined function. It's a function that's defined in pieces. All right, so let's go ahead and look at a few examples of a piecewise function. All right, so first of all, let's forget about a graph for just a second. Let's just talk about the equation and how it relates to the way we usually look at functions and plotting points and all that other stuff. So let's take a function, we'll call it g of x, and I'm going to define it in 3 separate pieces. Whenever x is less than negative 2, I want g of x to equal to, let's go with 5 minus 5 minus x. Okay. All right, but what if x is not less than negative 2? Well, if x is between negative 2 and positive 2, I want to go ahead and include negative 2 as part of this piece, but I don't want to include the 2 as part of this piece. Then it's going to behave like a parabola. Let's say x squared. And then, okay, well, that's what happens when x is less than negative 2. Here's what happens when x is between negative 2 and 2. What if x is greater than 2? Or in this case, greater than or equal to. Here, the 2 was not included in this part, so I'm going to include it in this part. And if my x value is greater than or equal to 2, I want it to behave like, oh, let's say x to the third minus 1. Okay, I'm not going to graph this one. I'm going to go ahead and look at this one from an algebraic standpoint, not from a graphical standpoint. Let's plug in some numbers. Remember how function notation works. Whatever number I plug in there, that's what gets plugged into my function. All right? Whatever the argument is, whatever number's in the parentheses, that's what I'm plugging in. Okay, so let me find g of 1. When I say, well, where do I plug it in? Look, I have a bunch of x's. Say, oh, well, wait a minute. I was told that whenever I have an argument, whenever I have a number in the parentheses, I just plug it in for all my x's. So let me do it there and there and there. That's not how this works. Remember, the function doesn't always behave like this. It doesn't always behave like this. And it doesn't always behave like this. Rather, these are the ones that tell us how the function behaves. So here, I want to plug in the number 1. Well, okay, well, where does 1 belong? Where does an x value of 1 belong? Well, let's see. X is less than negative 2. Is that what I have? Is that x value less than negative 2? No? Okay, well, then you're not plugging it in there. Oh, okay. What about 1 here? If x is equal to 1, is that between minus 2 and 2? Yeah, that's right. It is between minus 2 and 2. Okay, so then that's the one you're plugging it into. So here, g of 1 is equal to 1 squared, which is just the number 1. Let's try g of 2. Okay, if x is equal to 2, well, let's see. 2 is less than negative 2. Yeah, no, it's not. Okay, so then you wouldn't plug it in there. Okay, that 2, is that between minus 2 and 2? No. Here, look. I'm not including the 2 as part of this interval. Okay, so then it doesn't belong here either. Notice, if x is equal to 2, that belongs in this interval. Anytime x is greater than or equal to 2, that belongs here, which means this is the one I'm plugging it into. So g of 2 is going to be 2 to the third minus 1, which is 8 minus 1, and that's 7. Notice, this tells you, once you know what your x value is, this is how you can tell where it belongs. Oh, does that number belong in this interval? Oh, does it belong in this interval? What about this interval? Once you know what interval it belongs to, this is what's telling you what you're plugging it into. Let's say I had g of minus 1. Well, again, minus 1, is that less than negative 2? Is that in that interval? No, negative 1 is not less than negative 2. It's between minus 2 and 2? Yeah, it is. It's between minus 2 and 2. So I would plug negative 1 in this. It wouldn't go in here, and it wouldn't go in here. So this is negative 1 squared, which is 1. Try that. Here, use that exact same function here, using that g. Go ahead and try the following. Find g of negative 2. Find g of 0. Find g of, let's say 3. Go ahead and pause the video. And once you find all 3 of those numbers, go ahead and unpause and we'll go through them together. Okay. Negative 2. Is negative 2 less than negative 2? No, it's not less than negative 2. Okay, so it doesn't belong in this interval. So it means that you don't plug it in here. Is negative 2 less than or equal to negative 2 and less than 2? Yeah, it is right here. Negative 2 is less than or equal to x. Oh yeah, that's what I have here. That negative 2 is the very last number in this interval. Oh, well, then that means it does belong in this interval. So I'm plugging it into x squared. So here, don't plug it in here, and don't plug it in here. Just this one. So it's going to be negative 2 squared, which is 4. All right, let's try 0. Is 0 less than negative 2? No. Okay, then it doesn't belong in that interval, which means you're not plugging it into that function, or that piece of the function. Is 0 between negative 2 and 2? Yeah, it is. Okay, so you're plugging it into this one. So that's going to be 0 squared, which is just 0. All right, you notice you didn't plug it into the top one or the bottom one. G of 3. Is 3 less than negative 2? No, it's not less than negative 2. Is it between negative 2 and 2? No, that's too big. It would be bigger than 2. Oh, okay, so it's in this one. My x value is greater than or equal to positive 2. So I'm going to go ahead and plug that x value in right here. So it's going to be 3 to the third minus 1. 3 to the third, 3 times 3 times 3 is 27. Minus 1 is 26. And there we go. Notice, once you have an x value, first figure out what interval it belongs in. If it belongs in the first interval, you plug it into the first piece. If it belongs in the second interval, you plug it into the second piece. If it belongs in the third interval, you plug it into the third piece. It doesn't go into all of them because not every one of them is used all the time. This tells you when to use this piece. This tells you when to use this piece. And this tells you when to use this piece. Okay, finally, let's take a look at a graph. All right. Let's say we have a piecewise function. Let's call it f of x is equal to, let's have it equal to 2 minus x whenever x is less than or equal to 0. Let's have it be x squared plus 2 whenever x is greater than 0 and, I have that backwards, don't I? There we go. Whenever x is greater than 0 and whenever x is less than, let's say 3. And then let's have it be, let's say the number 5 whenever x is greater than or equal to 3. All right, that should work out nicely. So let's go ahead and graph this. Note, all of these are things that we know how to graph. This is a linear equation, y equals mx plus b. This is a quadratic. You use a parent function. Take your quadratic, move it up by 2. And here that's a constant. A constant function is a horizontal line. We saw that back in 2.3. So each of these can be graphed on their own. The trick is not to graph them on their own, but to graph them all together as a piecewise function. Well, really, you are going to graph them on their own. You just sort of graph them on their own together, right? Or they're going to be lonely together. Yeah? Okay. My x value, 0, 1, 2, 3, 4, 5. Negative 1, 2, 3, 4, 5. Okay. Notice that my function is going to behave some way when x is less than 0. It's going to behave a different way between 0 and 3, and it's going to behave another way when you have x values greater than 3. So here, there's going to be a change at 0, and there's going to be another change at 3. These lines that I've just drawn are not going to be part of our graph, but we're going to use them to help us break our graph up into the appropriate pieces. Because here, by drawing these two lines, one at 0 and one at 3, I know that when x is less than 0, in other words, when I'm to the left of this line, it's going to behave one way. When x is between 0 and 3, if it's between these lines, it's going to behave a different way. And when x is greater than or equal to 3, it's going to behave this third way. Just like that. All right, so let me go and put some y values on here. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. All right, so let's start off with 2 minus x. Okay, well, that's also the same as saying minus x plus 2, which means I have a slope of -1 and a y-intercept of 0, 2. All right, negative x plus 2, that's y equals mx plus b, right? Your m is your -1 in front of your x, so that's your slope, -1. And then your b is 2, which means your y-intercept is 0, 2. So here's my y-intercept. And let me do this one in pencil first. Here's my y-intercept, 0, 2. And then I have a slope of -1, which means I go down 1 and over 1, down 1 and over 1, like that. So I can go ahead and graph a line that looks like this. Okay, but that's not correct, at least not fully correct. Because notice, my graph doesn't always behave like 2 minus x. It only behaves that way to the left of 0. In other words, to the left of this line. So here, I've drawn this graph too far. It shouldn't behave that way forever. It should only behave that way from 0 to the left. All right, there we go. So this line keeps on going to the left, but to the right, it only goes as far as the y-axis. It only goes as far as 0. Okay, so what happens after 0? Well, now it looks like a parabola. X squared, we know what that looks like. X squared would start at the origin, and it would go up and over to the right, like that, and up and over to the left. Oh yeah, that's x squared. This is x squared plus 2. Oh, okay, so this is the translation. We saw in 2.6 that this is going to cause your graph to move up 2 steps. So from here you go up 1 and 2. Okay, there we go. So now that's this graph here. Okay, well yeah, but that's too much. Because, yes, that is the graph of y equals x squared plus 2, but it's not supposed to always behave like that. It's only supposed to behave like that between 0 and 3. So here, yeah, that is the correct graph, but I've made it too big. It shouldn't exist to the left of 0, and it shouldn't keep going once you pass this line. So it's only between here and here. Notice these two do connect, right? This one ended at 0, 2, and this one started at 0, 2. So it is possible for the pieces to connect where one leaves off, the other one can pick up. Okay? Notice here that this does not include 0 or 3. So here I'm going to use an open circle to signify the fact that this point is not part of the graph, only up to that point, but not including it. Now here, technically the parabola does not include this point, but this line does. So here, if you're being very technical about it, here this is an open circle for the parabola, but it's a closed circle for the straight line. Oh, but since they both meet up at the same point, really that point is there, right? It's there for just the straight line, but it is there as part of the graph. But this one is definitely not there, because look what happens for this piece. This is a constant function, y equals to 5. And we've seen that that's a horizontal line. 1, 2, 3, 4, 5 steps up. 1, 2, 3, 4, 5 steps up, yeah. That's a horizontal line. But again, that's too big. I only want that graph to exist to the right of 3, when x is greater than or equal to 3. So here, this is too much. I don't want this part back here. I want it to start at 3. Okay, so that point should be there. So notice that's an open circle. It's not included. That is a closed circle. The point is not up there. It's down here. And then to the right from there onwards. Notice that your graph can connect. One piece can pick up where the other one left off, but it doesn't have to connect. It's possible for there to be a big jump, a gap, a break in between your graphs. Remember, this vertical line here was there to help us separate the graph into pieces, but again, this vertical line is not actually part of your graph. So it's not like this connects straight down. Your graph is those pieces there. It's this linear equation that connects to this quadratic equation, which then jumps to this constant function. And that's our graph. Whenever you have a piecewise function that you're graphing, you graph each piece, but only in its respective interval. X is less than 0, so from 0 to the left only. It'll behave like that. X is between 0 and 3, so only between 0 and 3, it'll behave like that. And when X is greater than 3, so starting from 3 onwards, it's going to behave like that. If the two graphs connect, great. They were meant to connect. If they don't connect, great. They were not meant to connect. And that's it. So that is it for the section. If anybody has any questions, comments, or problems, please make a note of them, write them down, and reach out to me next time we meet. Or if you have my contact information, let me know, and I will get back to you as I can. I hope everybody has a nice day.